So welcome to another session of the Assumptional Physics reading group. I think we're still waiting for people to come on, or well, it's 11. Let's see. Do we have new people from the other time? I think so, right? Rob, you didn't come last time, right? Were you there last time?
Me?
Yeah.
Yeah, I was there.
You was there, okay. Was there anybody here that wasn't there? No, it's all people that were here last time. So I'm a little bit confused. Sorry. There were some people that asked to come, and but I don't see anybody new anyway. I don't see either. Let me see. Uh, Let me see. My reading group. Yeah, I don't even see Alina. But I think we have to start on time because we can't just have the live open. I mean, it would makes a little bit not so much sense. So we'll just jump right back to it. Does anybody remember what paragraph we were at? So we started the 1.2. Oh, I should share, by the way. Oops. And I should share this one. Yes. And I'll put the link in the chat so that if anybody wants to follow, they can follow directly from there. Okay. And I have to have an eye for people coming in. Otherwise, okay. I have to start understanding how to position everything. Okay. So I believe so we finished here. Were we at just 1.2?
No, I think we went past that a bit.
Oh yeah, we did look at this.
And then we finished
So we were
there,
here, right? Okay. Who wants to start?
Okay, I guess.
Go.
Okay.
Decisive.
We now want to understand whether all Lagrangian systems are Newtonian. Given what we discussed, we cannot expect to reconstruct the mass and force uniquely from the expression of the Lagrangian. We consider the mass and the frame fixed by the problem together with the Lagrangian, and therefore we must only see whether we can indeed find a unique expression for the acceleration. From the Euler-Lagrange equations 1.3, we can write the derivative of the Lagrangian with respect to the position is equal to the derivative time of the derivative of the partial derivative of Lagrange. Sorry. The partial derivative of the Lagrangian with respect to position is equal to derivative with respect to time of the partial Lagrangian with respect to position is equal to a complete mess. I'm not going to bother
Yeah,
speaking.
so I don't know if it makes sense reading the whole thing. Maybe we
Yeah.
can just, pause for a few seconds. I find that instead of saying derivative and so on, I would read something like partial xi equals derivative in time partial vi, right? So that's a little bit quicker, but I still don't think that that it makes sense doing that. I think we leave enough time for people to look at that. And understand uh, the steps, right? So if there is something unclear of the steps, what's happening, do ask.
Yep. So I'm actually not. So we expand. Okay. So we expand it, and then we get this del VK a del VI of Lagrangian. Um,
Yeah. So
eh,
you're basically, the Lagrangian is going to be a function of position, velocity, and time. So the partial derivative is also a function of position, velocity, and time. And so this is just the chain rule. You have a
yeah.
total derivative in time. Now you have the partial x and then the derivative x in time. Same thing here. And same thing here where you have the derivative time in time. So this is the first step is just the chain rule. Then here you're just saying that this is one, and you're saying that the derivative in time of the velocity is the acceleration, and the derivative in time of the position is the velocity. So that's what you're doing. And then this is just rearranging this side on this side, and then you have that. In fact, why don't I do this? The next time that there is a big equation like that, I'll just go ahead and explain like this so that we are on the same page.
Okay. Yeah. And then to be able to write the acceleration explicitly, we must be able to invert the Hessian matrix derivative with respect to Vk and partial Vk, partial VIL. As we noted before, this is exactly the condition for which the principle of stationary action leads to a unique solution, and we can better understand why. If it is not invertible at a point, the determinant is zero, and therefore one eigenvalue is zero. The corresponding eigenvector corresponds to a direction for which the equation tells us nothing, and therefore a variation of the acceleration in that direction will not change the action. This is why the invertibility of the Hessian is required in order to obtain unique solutions. What we find then, okay, I'll let someone else take this part.
Yeah, is it clear the argument there? Because to me, it was always mysterious why this Hessian had to be, positive definite, and that this was the quickest argument that made me understand what was going on. So if it's not clear, ask.
So you just need an acceleration, and you basically write the Euler-Lagrange equations such that that will be the steps you have to follow to find the acceleration from them. And
Yeah.
in one of the steps you need is just inverting the Hessian so that you can have the acceleration on the left.
Right.
And then you just have to invert it. Okay.
Yes. And the point is that if you have a zero, an eigenvector with zero eigenvalue here you would have a zero, right? So one of the component of the acceleration would be not determined, because you would have, you just have a constraint. This would become a constraint on the position of the velocity, and it wouldn't give you the acceleration. Okay, let's continue. Call the next one.
Who should do next?
Oh, you. The last reader should call the next one for the first.
Okay. Let's say Farhan.
Yeah, sure, I'll go ahead. We're starting from the paragraph after the equations here.
Yes, actually, you are new, right? Because you weren't here last week.
Yes,
Why don't you give us a
I'm
quick,
completely.
why don't you give us a little bit of introduction? Quick
Okay,
introduction.
I'll go brief because you guys have already started. So my name is Farhan. I am my passion is math, and physics has always been like, something alien to me in some sense. So I saw this project and I was interested since it's offering to understand things from axiomatic sort of approach. So that's why I was attracted.
Yeah.
So that's why I'm here. I am hoping that my expertise in math can help formalize things. If things aren't clear, I could probably help.
Very good.
Yeah.
So right now we're doing the part that is more physics, and if you get
Yeah.
lost, you should ask questions. But then after we have done all this part, the other part, the physical mathematical part, that's where the axiomatization is. So it might be that part is more interesting to you. So if you completely lose the interest at the end, I would suggest you to come back when we are here, because that's where we look at topologies and sigma algebra and things that are more.
I see. Yeah, that's a lot more in my sort of domain. Yeah. Yeah.
Okay, so start. What we find. You have the link, right, for
Yes,
the text.
yeah. I do have the PDF. Yeah. So what we find is that when for any Lagrangian system, which we assume to have a unique solution, we can explicitly write the acceleration as a function of position, velocity, and time. Therefore, we have an insight that is all Lagrangian systems are by nature Newtonian. Now we turn our attention to Hamiltonian mechanics, and similarly, we ask whether we can express the acceleration as a function of position and velocity. We have the following equation. Would you like to go ahead and explain it, sir?
I'll go through it. So the acceleration is the derivative of velocity in time. That's just the definition. And the velocity is the derivative of position in time. And if we have Hamilton's equation, the derivative of position in time is partial ph. And now we do the same trick that we did before. We just use the chain rule. So the derivative with respect to position, with the derivative of position with respect to time, same thing with momentum, and then the same thing with time. And so same, okay, Suma, question. Oh, Suma needs to be promoted to panelist. I will need, Tobias, maybe next time I'll have you be a co-host so that you can look at those things while I'm talking. Otherwise,
I'm sorry, actually, my
yeah.
name is Arvind. I didn't change my name. I should probably do that right now. It's my mom's account, actually.
It's okay. Don't worry
I'm
about it.
sorry for that. Actually, I'm a friend of Farhan here.
Okay.
Yeah, and I just intend to
Yeah,
join
so
the.
we're friends. He's the physics-oriented guy. I'm the math guy. So yeah, we both joined as a pair.
Yeah.
Okay. So there is also a question in the chat. Miguel, where is the reading group info available? Send me an email. You'll find me, Gabriele Carcassi. You can also, I'm very findable. Send me an email, give me a little bit of a description about yourself, and I'll give you a link to the Discord where all the information is available there. Okay, so
So what are we discussing?
okay, so why doesn't somebody give him up to speed on the chat while continue so that we don't interrupt the flow?
Cool.
Okay, so we have okay, so we're saying here we're just taking the derivative in time, so we're just doing the chain rule, and then we apply the Hamilton's equation again. So this is the derivative in time of position. It becomes the partial p of the Hamiltonian. This is the derivative in time of the Hamiltonian. It becomes the partial of the Hamiltonian with respect to position. And this is just the time and time, and that's it. So it's basically just a symbol manipulation, and you just know what is it that you are manipulating. Okay, so we go here, and who continues? Rudra, why don't you continue?
Okay, so this tells us that the acceleration is always an explicit function, but it is, in general, an explicit function of position and momentum, not of position and velocity. To change the expression, we need to be able to write the momentum as a function of position and
Wait.
velocity.
Where are you reading them? I'm gonna read it. Do I have a different text? I have this tells us that we can always write an explicit function for the acceleration.
And might be using the 2.0 instead of dev version.
That might be it, yeah.
Yeah, because I'm using 2.0.
Oh, okay. So it evidently the text was changed to clarify, and so I have something different here. Somebody else jump in. Alina, why don't you read?
Sure, I'm just going to read off your screen because I also have 2.0, but it's fine. This tells us that we can always write an explicit function for the acceleration. However, this is not enough. States in Newtonian mechanics are in terms of position and velocity, not position and momentum. For a Hamiltonian system to be equivalent to a Newtonian system, we need to be able to write momentum as a function of position and velocity and vice versa. Note that Hamilton's equations already give a way to express the velocity in terms of position and momentum. We just need that expression to be invertible, which means the Jacobian must be invertible. We must have, and there you have.
Yes. So here is this again this thing that is sort of interesting is that the partial derivative of the velocity with respect to momentum is the Hessian of the Hamiltonian with respect to momentum, and this has to be invertible. Therefore, the determinant has to be zero.
Different from zero.
Did I say equal? Yes, different from zero.
Right.
And
Is this the proof of the convexity of the function where we make the Hessian positive, or if I'm not wrong?
so this basically, it's not really a proof. It's that this condition, right? The fact that we have this invertibility condition is the same as this condition.
Right.
Right. So we haven't proved this. We just know that one implies the other and vice versa.
Right. So then, to be able to express momentum as a function of position and velocity, then we need a Hessian of the Hamiltonian to be invertible, that is, to have non-zero determinant, which is what the equation above says. And I should call someone, right? Who hasn't gone? Arvind, since you were talking just a
Yeah,
moment
I
ago.
got that. Yeah.
No, I think she was calling you to read.
Oh, I'm sorry. Yeah. So do I continue?
Yes.
Yeah. So to be able to express momentum as a function of position and velocity, then we need the Hessian of the Hamiltonian to be invertible, that is to have non-zero determinant. Note that we had no requirement for the Hamiltonian itself. For example, the Hamiltonian equal to 0 leads to the equations of the total derivative of the position coordinate with respect to time equals to 0, and also the total derivative of the momentum with respect to time equal to 0, which have unique solutions. Both the position and the momentum, both the position qit equals to a constant and the momentum pit equals to a constant are constants of motion. The Hessian, being the zero matrix, is non-invertible, and in fact we cannot write momentum as a function of position and velocity. Velocity, which is the derivative of the conjugate variable, is also always zero in all cases, while the conjugate momentum can be any value kpi. Though this case may not be physically interesting, it is a perfectly valid Hamiltonian system and shows that we should always check the trivial mathematical case. However, let us go through a more physical, meaningful case. Yeah, think. So here, what they're basically talking about, should I explain that as well?
No. Just call somebody else. Like if there are no questions, we just continue.
Are there any
call,
questions here?
You have questions? No, just call somebody else to continue reading.
Right. Rowley, if that's right, you can start. Continue, I guess.
Nope. I've already read Kamat, maybe?
I see.
Rudra?
Okay. Probably Robert.
Hello. Okay. Photon as a particle. If we want to treat the photon as a classical particle, we can write the Hamiltonian by expressing the energy as a function of momentum. Do you want to explain that, or should I just read it?
You can explain it.
So yeah, energy equals h bar times omega. And then you can make omega c times the wave number. And then that's the same as c times momentum. If we apply Hamilton's equations, we have d sub t of qi equals c pi over the absolute value of pi, and d sub t of pi equals 0.
Okay, so this is just applying Hamilton's equation, right? The derivative of the position in time is the partial derivative with respect of momentum, and here momentum is here the Hamiltonian is the absolute value of momentum, and the derivative of the absolute value of momentum is momentum over the absolute value. And then the derivative of the Hamiltonian with respect to position is 0 because there is no position dependent. So this just applies the Hamilton's equation.
That is, the norm of the velocity is always c. The momentum decides its direction, and the momentum itself does not change in time, as shown in figure 1.1. Should we look at that? This one?
Yes. So this is the phase space diagram. If you guys have ever seen it, you put a position of momentum, and this is the vector field that tells you where the states are going. And so essentially, if you are above, if momentum is positive, you're going right in terms of the position, and you're below, you're going left. But note that the vector field is the same. So this means that the velocity is constant all up here and all up here. And this is the Hamiltonian. The Hamiltonian will be the absolute value of P. So as you increase the Hamiltonian, P increases the absolute value. So it's kind of funny because we're doing, the Hamiltonian for a photon, which you would think, well, it's a quantum thing, but you can actually write the Hamiltonian in classical mechanics, and it kind of makes sense. And it has to, because otherwise you wouldn't be able to make the quantum correspondence anyway.
This is indeed the motion of a free photon. One can confirm through tedious calculation that the determinant of the Hessian is indeed zero. Yet it is easier and more physically instructive to see that we cannot reconstruct the momentum from the velocity. Relativistically, all photons travel along the geodesics at the same speed. Therefore, two photons that differ only by the magnitude of the momentum will travel the same path. And let's see. Can actually see everyone now at once.
Yeah, next time we'll just write in the chat directly an order, and we'll do that. This is not working.
I think Tobias. Is that her?
Tobias.
Yep. Tobias, sorry.
Yes, thank you. Hamiltonian systems that are also Newtonian then need to satisfy this extra condition. So let us give it a name. Assumption KE, or kinematic equivalence. The kinematics of the system is sufficient to reconstruct its dynamics and vice versa. That is, specifying the motion of the system is equivalent to specifying its state and evolution.
Why don't you just go finish the section?
Okay. By kinematics, we mean the motion in space and time, and by dynamics, we mean the state and its time evolution in phase space. We will need to analyze the difference between the two more in detail, but we should first finish our comparison between the different formulations. Summing up, we find that not all Hamiltonian systems are Newtonian. Only those for which KE, kinematic equivalence, is valid. Okay, so I think next will be Ruda. Yeah. Ruda, you are the last one in the chain.
Oh, sorry. Yeah, just saw the order. Okay, so Lagrangian versus Hamiltonian. We will need to compare Lagrangian and Hamiltonian systems. The task is a lot easier because we already have a precise way to connect the two. If we're given a Lagrangian L, we define the conjugate momentum Pi is given by the partial VIL, and the Hamiltonian H equals Pi VI minus L. If we're given a Hamiltonian H, we can define a Lagrangian L equals Pi VI minus H, and a velocity Vi equals time derivative of Qi equals partial Pi H. However, this is a bit misleading. The above relationships connect the two connect the values of the functions for each state S. That is, L of S equals Pi of S times Vi of S minus H of S. Both the Lagrangian and the Hamiltonian are functions of specific variables. So we have to make sure we can express them in the appropriate variables.
Okay, there is a question from the chat that I missed before. If a Hamiltonian is a Newtonian, then the force will always be the gradient of the potential. There is no constraint that the Hamiltonian is kinetic energy plus potential energy. So, for example, the Hamiltonian for a particle in a magnetic field, a charged particle in a magnetic field, is a little bit more complicated. So, the relationship between forces and a Hamiltonian, it's something that you have sort of to look specifically in the case. I don't have right now like an expression, but it should be related to this. Here we have the acceleration as a function of the Hamiltonian. And so, if you imagine that you multiply this by a mass, and this is multiplied by a mass, now this would be the force. And so you see that it's a little bit more complicated than, in general, it's a little bit more complicated. If you have the usual, 1/2 p square over m plus the potential, then you would see, if you made the calculation, that the things would simplify to the gradient of the potential. So hopefully that was clear.
Going from a Hamiltonian to a Lagrangian, it again means that we can write momentum as a function of position and velocity, and therefore kinematic equivalence must hold. This makes sense if all Lagrangian systems are Newtonian, and Ke was required for a Hamiltonian system to be Newtonian. It is also required for a Hamiltonian system to be Lagrangian. But the connection is stronger. It's the only additional assumption we need to be able to write a Lagrangian given a Hamiltonian.
A follow-up from the chat. I should probably wait that the problem of the chat delay is always okay. So from a Lagrangian point of view, I get it, but from a Newtonian, you usually start with the force. Yes. So this will be more clear later because in principle, you can write a Hamiltonian for a system where forces are not well defined. So as the silly example, right? If I put h equals 0, right? You would have that the position is constant and the momentum is constant, and the momentum could be anything that I want. Now, this is clearly not a Newtonian system, right? It would be a system such that the velocity is constant, but the position is constant as well, right? That you can't have a non-zero velocity and then the position remains the same. So there are things in Hamiltonian mechanics that you can write that are not strictly things that are going to be a Newtonian system. And that's where there is basically this mismatch. In the standard case where you just have potential forces, everything collapses in the same thing. But it's in these different cases that things are a little bit different. So I hope, Miguel, this makes it more clear. Let's wait for a notification. And this is going to be the graph at the end. So that's why my initial assumption, if a Hamiltonian is Newtonian, then yes. It's just that not all Newtonian systems can be, not all the forces in Newtonian system come from a scalar potential. As I said, the magnetic force, for example, you have the Lorentz force, right? And the Lorentz force, it's what is it called? The vector product with between the velocity and the vector potential. So not all forces are gradients of a potential. Okay, good. Yeah, you should definitely jump in because it's a lot easier to have this conversation in person than with the chat. Okay, so I'll give you the information for next time. So I'll shut up and somebody should continue.
Yeah, I guess it's my turn next. Rolly, right? So, okay, all right. So going from a Lagrangian to a Hamiltonian, it means that we can write velocity as a function of position and momentum. Note that we can define the conjugate momentum as a derivative of the Lagrangian. We can already express momentum as a function of position and velocity, which means we're simply asking if the expression is invertible. This is again assumption of kinetic equivalence, just in the opposite direction. We have that our determinant of the derivative. Okay, I'm not sure how to read this. I will let you explain because I'm still getting used to all the notation in physics. So
Yeah,
it's
yeah,
a
yeah.
bit confusing for me. Yeah.
So this is basically the partial derivative of the momentum with respect to the velocity. So this is going to make a matrix because there are two indices, I and j, and you're looking for that determinant and say that it's different than zero. Now, because conjugate momentum in Hamiltonian mechanics is defined as the derivative of the Lagrangian, now this becomes the determinant of the Hessian of the Lagrangian. And there is a question. Arvind, you can just ask the question directly in voice.
Yeah, no, I was just thinking, why should the derivative of the Lagrangian be cross? Like, why should you have an I and a j component?
This?
Yeah, that
This,
term.
right. This is the matrix made by all the possible permutation of the second
Oh, you
derivative.
mean a Hessian?
Yeah, it's a Hessian. Yeah.
Ah, okay, got it.
Right. So the important thing is that these velocities are different. Like this is I and this is j. Right. These are
Right,
different
right.
indices. So you can imagine it as the 2 by 2 matrix where you're getting all the double derivative in all the permutations.
Yeah, thank you.
So in principle, momentum is a function of, so for a Lagrangian system, we consider the state to be position and velocity.
Yes.
So the momentum in this case is a function of position and velocity.
Yes.
So we, in principle, would just want, given a Hamiltonian state, meaning position and momentum, finding the velocity, right?
Right.
Why do we only care about these derivatives, not about like position, if that makes sense? Like I'm not 100% sure how I would like
Okay. Because the position is the same both in Hamiltonian mechanics and Lagrangian mechanics.
Yes.
So you don't need to make an invertible map there because it's the same map.
Well, yeah, this is pretty given. Okay, and I just need that basically locally if my velocity changes, my momentum has to change as well, or something like that.
Right, because at that point, if you're changing the velocity, right, you're only changing the momentum on the other side. You're definitely not changing the position. So you need that
That's the argument.
every time that you fix the position, you have an invertible map between the velocities and the momentum.
Okay. Yeah, that's what I was missing. Thank you.
Right.
Should we put that as a comment somewhere? I should probably make a list of this. So that might be something that it might be helpful to actually add.
Yeah, of course it was the same issue like before, right? It's
Right.
just
So
like once.
I would put it before, yeah. So
Yeah, I think clarifying the difference between position and velocity and Lagrangian mechanics and position and momentum would be very like I'm still confused on that, but
I
Good.
think we also invoke the momentum to really understand geometries and phase space. It makes life much easier because we are graphing between the the displacement coordinate, which is q and p. So writing the Hamiltonian and QP space makes things easier, I feel.
Yeah, but here it was just a matter of understanding why this, the invertibility is only between velocity and momentum, like when we are changing the coordinates. That's
Right.
why that what was the question was, and it's one of those things that I thought about it so many times that maybe it's obvious to me, and somebody coming from the outside, it's might not see it as obvious. So I'll add a comment beforehand. Okay,
Sure.
so where were we?
Right here at the top of the page, I think. So this means that the assumption of kinematic equivalence is exactly the invertibility of the Hessian, the condition for unique solution of the Lagrangian. All Lagrangian systems that emit unique solutions then satisfy the assumption KE. In fact, we can see that the Hessian determinants are related. And this is the relation.
Okay, so this is sort of the main point. You have the Hessian of a Lagrangian on one side, which is the sort of the Jacobian essentially. This is the Jacobian matrix because it's the change from momentum to velocity, right? We're doing a change of variable and then doing the infinitesimal change and see what happens. And now this is the inverse of this because this we're writing the momentum as a function of velocity. Here we're writing the velocity as a function of momentum. So these two matrices are one the inverse of the other, and therefore their determinant is just one, is just the inverse of the other. And then we saw before that this, because this is the velocity, is just the partial derivative of the Hamiltonian. And so the determinant of this Hessian is the inverse of the determinant of the Hessian. Of this Hessian. So this is different than zero if and only if this one is different than zero.
So this comes from the fact that you can switch the variables in Jacobian, and that's how you get the inverse Jacobian matrix, right?
Yep.
All right. Okay, cool. Okay.
So it's a very simple condition in retrospect, right? Before it's there are all these Hessians, but then you say, oh, I'm just inverting a matrix, and of course I can.
I wonder if we can derive this from the fact that like one is the Legendre transform of the other, like H and L are related by that. I still don't know. I still don't understand exactly why like the Legendre transform is used here, and then it's used again in like StatMech for like something completely different. I figured out like people in optimization problems use Legendre transforms to somewhat rewrite the optimization problems. And like a minimization problem turns into a maximization problem, which smells like this, where you turn like convex, like you flip it, right?
Yeah.
I don't know. It's a bit opaque, but I don't know. It looks very interesting. There's probably something.
I think mathematically what's happening is by means of this Legendre transformation and the hyperregularity condition, the Lagrangian mechanics which was on the tangent bundle, we have a fiber derivative into the cotangent bundle where the momentum is.
Yeah, that is true. You switch from tangent bundle to cotangent bundle, right?
Yeah.
Yeah.
Yeah,
Going from
it's just
Lagrangian
that
to Hamilton.
I also don't have a good geometrical way of seeing it because in principle, when you're doing the Legendre transform, you're taking the tangent and then you're looking at the intersect, like all of that stuff, right? In principle, there should be a geometrical intuition. I don't have it here. I don't have it either. So
I mean, you have the Poisson bracket, which is nice. I mean, the entire algebra of your dynamics is the Poisson bracket because when you quantize, you're just looking at the representations of the Heisenberg algebra.
Yeah. So that part I understand. Like the math of that I understand. I understand even the cotangent bundle and so on as mathematical concepts. But then what I'm missing is the geometry, the picture, like to have the intuition of how all these things sort of are related to each other. I understand the structure of the symplectic and the Poisson bracket. We'll see it later. We have a physical meaning for that. I don't have a physical meaning for the Legendre transform, except that I can mathematically recompute it and see that it's there because we're gonna get it later. So.
Since you mentioned symplectic, actually, when I did this, I had a confusion. How is it even related to symplectic geometry?
We'll see it later. Let's
Sure.
yeah. So we'll just talk about it when we actually see it.
Cool. So I think I have to read. This means that every Lagrangian admits a Hamiltonian, but not every Hamiltonian admits a Lagrangian. Only the Hamiltonian systems for which the kinetic equivalence is valid will also be, kinematic equivalence is valid, will also be Lagrangian systems with a guaranteed unique solution, given that the kinematic equivalence is exactly, can you go up? Yeah, is exactly the assumption needed for that as well. Therefore, we conclude that the Lagrangian systems are exactly those Hamiltonian systems for which the kinematic equivalence is valid.
So is validity here this unique solution?
So we saw that the condition for a Lagrangian system to have a unique solution was exactly the fact that the Hessian, the determinant of the Hessian was not zero.
Mhm.
So the Lagrangian system that have a unique solution, which I would basically call the Lagrangian systems, are exactly the one for which you can also write a Hamilton. So
Yeah,
there are
okay.
no Lagrangian systems that have unique solution. There are not also Hamiltonian systems. And then, of course, there are Lagrangians that do not emit a unique solution. And then whether those are actually Lagrangian systems, you have to, argue or not. Like in this case, we're basically not considering a Hamiltonian system because otherwise you open up to Lagrangians that basically tell you nothing. As we
Right.
said, like last time, if you take the Lagrangian is equal to 0, then all the paths have the same action, and therefore all paths make the action stationary, and then you're basically saying, yeah, all paths are possible. And I don't think you have a physical system at that point because you can't say anything. So
Okay, thank you. Relationship between formulations. The relationship between the different formulations then can be summarized with the Venn diagram in figure 1.2. Not all Hamiltonian systems are Newtonian, and not all Newtonian systems are Hamiltonian. All Lagrangian systems are both Newtonian and Hamiltonian. We have found that kinetic equivalence is a constitutive assumption of Lagrangian mechanics, and that it clearly marks which Hamiltonian systems are Newtonian or Lagrangian. By constitutive assumption, we mean an assumption that must be taken either explicitly or implicitly for a theory to be valid. But what makes a system Hamiltonian and what makes a system Newtonian? Can we find a full set of constitutive assumptions for classical mechanics? Tobias?
Yeah, thank you. Kinematics versus dynamics, which I guess is space and space. We have
yes,
seen.
trying to see whether it makes sense to start. Well, let's start and then we'll see. I'm a little bit hesitant because it's going to be something that we review, but maybe we can start reading and then that's what we should do. Next time we'll give a brief recap of the section that we had already started. Okay, so we're figuring out how to do this.
And also, I guess, tangent bundle, cotangent bundle, but I don't think we're going to get into that.
No, not here.
We have seen the importance of the connection between kinematics and dynamics. In this section, we will explore this link more deeply and come to the following conclusion. The kinematics of a system is not enough to reconstruct its dynamics. Is the figure already related to that?
No, the figure is actually for a solution later, so we should leave it. But there is a question from Miguel from the chat. What do you mean by a theory to be valid? Are physical systems the only one for which a KE holds? So a theory is valid in the sense that it's applicable, right? So we have seen that there are some systems that are Newtonian systems that I can study within Newtonian theory, but I'm not going to have Lagrangians for. So for those systems, right, then the Lagrangian system, the Lagrangian theory would not be applicable, and so it's outside what you can do with that. And so the general idea is that you have physical systems in the world that you're studying, and then you have a bunch of different physical theories that you can choose from, and you have to choose the correct one to study the correct system. So if you're studying the pressure and the volume of an ideal gas, right? You are not going to use Hamiltonian mechanics to describe the conjugate relationship between pressure and volume. Like that's the theory in that space is not applicable. It's not valid in that sense.
Is there some meaning to the how much larger the area is that is exclusively Newtonian systems, or is that just
a little bit in the sense that, I mean, it's one of those things. So if you remember the argument for saying that the Newtonian systems there are more Newtonian systems than Lagrangian system is that, if you increase the number of degrees of freedom, you have n arbitrary function for Newtonian system and only one arbitrary function for Lagrangian system, right? So in principle, there are a lot more Newtonian systems that are not describing by Lagrangian system. But then, what does it mean? A lot, would have to put a measure on the space of this. Like, it just doesn't make sense. But yeah, and the systems that are Hamiltonian but not Lagrangian, apart from the photon as a particle, right? I don't know of anything else that would be significant, and you would actually be interested in, right? So in principle, this area should be even much smaller. So basically, should be a sliver because I don't think that there is anything interesting. So there is kind of something like that, but yeah.
Cool, thank you.
So the probability of having a Lagrangian is really high, like for any system. Like
Say that again?
the probability of finding a Lagrangian for any system is really high, right? According to this.
I don't understand the question, sorry.
The probability
The
to
probability.
find basically for any system, you can find a Lagrangian much easier compared to a Hamiltonian or a Newtonian.
Now, the point is that you are not going to have a Lagrangian for all systems. So there are systems for which the Lagrangian does not exist.
Like?
Well, we're going to see it later. That's kind of for now, we just seen that there is an existence, right? So there are more systems here because we can parameterize this in a much bigger space than this. That's the only thing that we know so far. Then later, we're going to see what's happening. Right? One thing at a time.
Was the photon in Hamiltonian mechanics, wasn't that an example?
Oh yeah. For example, yes. So the photon as a particle that we saw that it's a Hamiltonian system that does not have a Lagrangian because you can't invert the relationship between position and momentum. Thank you, Robbie. You're right. I was thinking on this side, but we gave an example on this side. Yes.
I mean, the other side is just a force that doesn't come from a potential because a Lagrangian is like kinetic energy minus potential energy. If you have a force that doesn't have a potential, you cannot find
Right.
that.
So basically, you need a deterministic and reversible force, but that's what we're going to find like in two chapters. I mean, if we always look ahead, then we are always like repeating the full section, the full chapter every time, which I don't think is useful. So we should go in order. Okay, so who was next?
I think it was me.
Go ahead.
Particle under linear drag. Let us first review exactly what the kinematics and dynamics are. Given a system, its kinematics is the description of its motion in space and time. Position, velocity, and acceleration are kinematic variables because they describe the motion. Kinematics is what Galileo studied and started to give a rigorous account of. The dynamics instead describes the cause of such motion. Force, mass, momentum, energy are dynamic quantities as they are used to describe why a body moves in a particular way. Dynamics is what Newton introduced, and his second law, expressed as F equals ma, clearly shows the link.
And by clearly shows the link, I mean that on this side, this A is a kinematic variable, and then F and M are dynamical variables. So the mass is also what allows you to go from one thing to the other.
Yeah, so I'll go ahead. The link between two concepts seems important given the constitutive role of Ke in Lagrangian mechanics. Moreover, both Newtonian and Hamiltonian mechanics are dynamical theories in the sense that the quantities like force and momentum are intrinsic parts of these respective theories, whereas Lagrangian mechanics seems to be purely kinematic, as it is described only by kinematic variables like position and velocity. Therefore, it seems useful to characterize kinematics and this kinematics and dynamics link as much as possible. Let's analyze a concrete example. Suppose we're given the following equation: ma is equal to minus bv. The equation in terms of kinematic variables and given initial conditions x naught and v naught, it admits a unique solution and a unique trajectory. The solution, as plotted in the earlier diagram 1.3, is x of t is equal to x naught plus v naught m by b into 1 minus e to the power of minus b by m into t. V of t is equal to v naught into e to the power of minus b by m into t a of t. Okay, so we're just taking the derivatives over and over. I have a question though.
Yep.
I'm not sure how E just pops up. Like maybe I'm missing a lot of physics background.
No,
but
it's so this A is the acceleration. So this is the derivative of the velocity with respect to time.
yeah.
Okay, so now you have just a
Okay,
first
makes sense.
order
Yeah,
linear
okay, I get it.
equation, and the
Yeah,
solution
you
is
just take
just
B to the
the
other side.
exponential.
And, yeah.
Now that we have
Yeah,
the
cool. Okay,
exponential
got
for
it.
V, the position
Right.
is just so velocity is the derivative of position in terms of time. So then the position is just the integral of this, and that's how you get this expression.
Yeah.
And the acceleration is just the derivative of the velocity. So again, you get the b minus m outside, and you get the acceleration. And these are the graphs. So you can see again, because we have this equation and we have minus b over m, which is negative, the velocity will go down like an exponential. That's why this is basically a system in friction. So the velocity will decrease until it never really goes to zero, right? It goes asymptotically to zero. And this is just the integral of that. So x0 is going to be the initial condition. And then we're going to stop at the position, and it's going to be x plus basically the change given by the initial velocity. And the acceleration is always negative. Like if you start with a velocity, whatever the velocity is, then the acceleration will go down because it progressively slows as the acceleration decreases as you get slower. Right. So this is the solution.
Yes. So next is Alina.
Right. Can we reconstruct the forces acting on this system? The obvious answer seems to be that the constant mass represents the mass, constant m represents the mass of the system, and F equals minus BV, the force. This is the case of a particle under linear drag. The system is subjected to a frictional force that is proportional and opposite to the velocity. If we set the Lagrangian L is equal to 1/2 mv squared times e to the bm on t, and apply the Euler-Lagrange equation 1.3, we have this point.
Right. This is just pure calculation. So if you remember the Euler-Lagrange equation, it's basically this minus this equals 0, but I can always write it like this, and this equals on the other side. and then this is just pure computation. Like you take the Lagrangian, you do a derivative in the velocity, so the velocity it was square, and it simplifies with the 2, and then you take the derivative in time of this, which is simply the derivative first in terms of the velocity, so it gives you the acceleration, and then you have the derivative in time of the exponential, and so again you get to the b over m here, which simplifies with the b, and now you can collect the exponentials, and now you have the exponential ma plus bv, and this has to be equal to 0, so which means that ma equals minus bv.
Right. Therefore, we have a Lagrangian for the system. We can also find a Hamiltonian. And you write as b equals partial VL, which is mv.
So this is just, again, we're applying, we take the Lagrangian, the momentum is simply the derivative of Lagrangian with respect to velocity. So we have this, and that's going to be mv e to the bm over t, because we're just taking these 2 and simplifies with the other 2. Then we invert, now we write the velocity as a function of momentum, and now we can write the Legendre transform. H is equal PV minus L, and so the V, we can substitute it here, and now, and you also substitute the Lagrangian, which was this other element here, and then you just make the calculation, and you're gonna get a 1/2 PV or p squared over m, and note that the exponential here is with a minus, while this in the Lagrangian was with a plus. So kind of this was like kinetic energy multiplied by an exponential with a positive, and this is kinetic energy with a minus.
And you apply Hamilton's equations, and
yeah, and so you get this Hamilton equation. There was a question in the chat, maybe a question later. I think, so this is kind of the problem. This becomes very mathsy, and I think it makes just sense to stop and to review these things for next time, because you are gonna have to have so the only reason why we have this equation is to see that they don't work. And so we need to see, to arrive to the end and then see the new graphs and see how they don't work. And we're gonna get out of time. So I think I'd rather spend the last 3 minutes answering from question, especially because there's one in the chat. Is kinematic equivalence also applicable to open system, time-independent system, or equations of motion where higher order derivatives are included? Let me think about that. Yes. So if you can imagine that you do have a map between conjugate momentum and velocity, right? For example, if you are in an inertial system, the map is always going to be that the momentum, conjugate momentum P is equal mv, right? And so you have a map for conjugate momentum to velocity. And that map is valid even if you have an open system, even if you have friction or anything else. Like we are still going to have that map.
But when it comes to high derivatives, wouldn't that mean like our state is position, velocity, and acceleration, or whatever order you're going to? That was the second part of this question.
Oh, the second part of the question. Equation of motion where higher order derivatives. Yes, okay, you're right. If you have higher order derivatives, that it would mean that the state of the system is not fully defined by position and velocity. And then you are already outside the realm of Newtonian mechanics and in general classical mechanics. Right? You need to have something else. There are some cases in which those higher derivative can then be reframed as actually a position or velocity of something else, and that you can recover. But it's basically not true in general that any any equation, even any total differential equation in time, is a classical system. Like you need the state to be described by position and velocity.
So that's what we mean by kinematics. Like in principle, the kinematics is the full trajectory.
Yeah.
Right. So in principle, you could consider like the velocity, which is also defined on an any arbitrarily small open interval, I guess. You could also consider that to be it is a kinematic variable. It could, in principle, be used to define, like we could consider a system where the state is defined by also the acceleration, and we would still call that a kinematic, a
Right,
system where the state is defined by kinematics.
Right, but you wouldn't have kinematic equivalence because the kinematic equivalence here is that you're going to be able to reconstruct the momentum. Like you can go from momentum to velocity and vice versa. So
Yes, so this is explicitly what we call kinematic equivalence, even though some
correct.
people might say, well, actually, this is still kinematics, just one higher, like one more term.
Right, but then if you fail to recover the dynamics, like your momentum and energy, all of that, they cease to make sense
Yeah.
because yeah,
I wouldn't know of like a Hamiltonian that would correspond
you
to
wouldn't
that.
have a Hamiltonian that corresponds to that, yes,
Okay.
or at least not in this way, right? Again, mathematically, you can always take any system of equation, double up the variable, and then you say that you have a Hamiltonian system. You can always do that, at least locally. But it's not what we mean by kinematic equivalence.
Yeah.
Did you explain why equation 1.18 is the Lagrangian for a particle
So
under drag?
the whole point next is to show that this is not actually the Lagrangian. So what I can show you is that if we set this Lagrangian, it seems that we're going to get the same equation of motion.
Okay.
And so the whole of the chapter is going to be, yeah, you can do it, but actually that's not what you are actually doing. And the reason why I have this chapter is because this is actually a point of confusion even in people that, that publish papers. Like there are people that try to use a Hamiltonian like this. There you go, this. And then you say, oh, I put this Hamiltonian in quantum mechanics and I am quantizing a dissipative system. That's not what you're doing. And there are even weirder Hamiltonian that you can sort of. There is another Hamiltonian that works for a damped harmonic oscillator where you basically use the logarithm, and so you don't even have the time dependence. But then basically you're throwing out all the momentums that are less or equal to zero because you have a logarithm of the momentum. So clearly that's not the standard momentum. It's you're doing something different. So the whole point is to show that you can write some of these things and they kind of work as a mathematical curiosity, but you're not getting the physics right.
Okay, sounds good.
So that
In
is
general,
why I
when we
was a
have
little bit skeptical in starting this chapter because this chapter with this section because you have to see it through the end. So anyway, sorry, Rudra, go ahead.
No, all I was gonna say was in general, when we have a dissipative force, don't we usually consider like a Rayleigh dissipation function in the Lagrangian rather than just adding the
Right,
velocity
that's
like that?
a way to modify the Euler-Lagrange equation to allow for a certain class of dissipative systems. But there are a lot of other dissipative systems that do not fit that framework anyway.
Okay, makes sense.
Yeah, I'm actually futzing around with a mathematician that mainly does fluid dynamics, but he contacted me because he had an intuition of how to extend our interpretation of the principle of least action to dissipative system. And so now we're basically trying to futz around to find a variational principle that would also give us the Rayleigh potential and hopefully even more dissipative system, not just those. So yeah. Any other questions, comment, or things people want to discuss? Okay, so we'll stop it here and see you all next week, and we'll go back at 10 a.m. EST, which is other appropriate times in various time zones. Okay, bye guys,
Thank
and
you.
bye to everybody
Thanks,
that
everyone.
was
Bye.
following online,
Goodbye.
and see you next time. Oh, there's a question from Miguel, chaotic system. So there are a chaotic system actually in Hamiltonian mechanics. There are some systems that are Hamiltonian, but they're still chaotic. And again, it doesn't change anything for our purposes. Like there is nothing that we are doing that that limits the fact that you have chaotic systems. So in that sense, I've thought about them, but I don't have any specific characterization. We're not going to have a specific characterization for chaotic systems.
They are still, I mean, we will get into this later, like deterministic. They are also reversible,
Yeah.
I guess, because still like phase space volume is conserved. But in practice, that doesn't help you because like any phase space volume you start with becomes something like a fractal or something like that. And you
Yes.
can, right, really invert it.
Yes.
So it's
And
like covered, but
you
it's
also have a problem that you might even have a trouble to know what the map is, because if the map is chaotic, like even knowing that you have the right map might be difficult. But if on the other
wrong map.
side,
Are you talking about like a time evolution?
yeah. So the
Yeah.
Hamiltonian itself, right? So if a Hamiltonian is chaotic, means that you change a little bit your position of momentum, you have a radically different energy, right? And or that the evolutions are going to be all over the place. And now think that you have to actually experimentally test that you have the correct map, right?
Yeah.
Like the
But isn't it
uncertainty.
locally, like the Hamiltonian is like something like infinitesimal time translations, like a generator of time translations, which by the way is something I don't know how to formalize, but I just keep hearing this. Anyway, so like for small time intervals, like chaotic systems are like easy to characterize, right? I mean the the chaos shows on like in a limit of like long times, or not? Is it not right?
I think it gets more difficult. Like
Over time.
when we actually develop I mean, when we actually transform coordinates for a Hamiltonian system, there is something called a canonical transform. And when we actually do that for a when we actually perform a time-dependent transformation, which is a chaotic system, it's
Mhm.
actually not easy. You need to solve Taylor expansions and all of those things.
That basically tells you that doing a time evolution, doing a time evolution or doing the coordinate transformation in time is sort of equally as hard, right?
Yeah.
And so that's basically the same reason why I'm saying it's difficult to measure the Hamiltonian, because if you think about it, measuring the motion means saying, I know where I am right now, I have to tell you where I'm later. And the Hamiltonian is exactly what it's telling you what's going to be that difference. And now if you have a high uncertainty in your measurement on the final position given the initial position, because if small changes in the initial position, the final position is going to be very varied, then you also have a higher uncertainty of understanding what the Hamiltonian is. And Tobias, it might be that for a short time scale, you have less chaos. It is true, but
Yeah.
longer time scale would be exactly what you would need to know more precisely what your Hamiltonian is, right? Because suppose that I want to measure the mass. Let's say I'm just have one half p squared over m. So the only thing that I'm trying to measure is the mass, right? of course, if I let time go more through, like go longer, right? I can see sort of the angle between the position and velocity better, and then I'm gonna be able to measure the mass better as well.
Mhm.
So, right, because the mass is gonna tell you how the system is gonna evolve in the future.
So I thought if you just prepare a system at one point in phase space, and you just like you only need the first derivative at each point in phase space, you need your displacement field in the whole phase space, right? And once you have that, if it is a Hamiltonian system, you can
Yeah,
find
but
Hamiltonian.
you have an uncertainty on the initial position and the uncertainty on the final position. So now,
Um,
if those two things are too close to each other, you're not going to be able to measure the change effectively.
okay, so
True.
what I was thinking is like if we had a perfect point and
Yeah,
I
if you
could
have a
just
perfect point, you can
yes.
do everything. But
But of course, okay, the point is like if I have like bounds on initial conditions and then I let it evolve
yeah,
and get some other volume, what kind of constraint do I get on some space of Hamiltonians, I guess?
yeah,
And then you're saying like it's gonna be huge.
yeah.
Okay, that makes more sense.
Anyway, Miguel, the motivation for my question, does KE hold for chaotic dynamics? Yes. So, as I said, there are Hamiltonian systems that are chaotic, and we saw that all, well, some, so, okay, technically, I haven't said that, but yes, there are Newtonian system and there are also Hamiltonian that are chaotic. So you're going to have some system for which you have chaos and which K will hold, and you're going to be able to write a Lagrangian for it. The fact that these things are not discussed when you do chaos theory, because typically when you're doing chaos theory, you're not thinking really of mechanics. You just have a system of equations, right? So you have your state variables, and you have your equation of dynamics that tells you what is the first derivative in time for all those variables, and then you study things. So a lot of the system that you study in chaos theory are not Newtonian systems. They don't come from mechanics. So one of the systems that I recall studying was the prey-predator system, right, where you have two state variable, the predator and the prey, like, that tells you how much you have, and then you have a nonlinear dynamics between those things, and then depending on the parameters, you can, you have a stable equilibrium, then you have the circle equilibrium. I don't remember if you can get chaos, but these are the type of things that you do in dynamical system.
I think so. Is it the famous Feigenbaum constant thing where you have like a bifurcation happening?
Yeah, you have a bifurcation, and it's the
Yes.
circle, and then you bifurcate again and again.
Yeah,
Yes.
that's right.
Okay, so in the predator model, not. So yeah. Anyway, the point is that those systems where you can have chaos and you have a bifurcation of that, they're typically. In fact, if I remember correctly, there is a chaotic system. Oh no, that was discrete. So I knew that there is in a discrete. You only need one state variable for making a chaotic system that is discrete, but you need at least two for making in the continuous case. But the point is that you can definitely have systems that are not coming from mechanics, and most of the systems that I've studied in dynamical systems and therefore chaos theories, they were like in the realm of dynamical system. They weren't from mechanics, and so typically when you study things in physics, you're doing mechanics. You are not studying a chaotic system, not just because not
Were
because
you
they
talking
don't.
about the Wang-Chen's system?
What?
When you were saying that you only needed one state variable, is it the Wang-Chen system?
I don't remember the name.
Ah, okay.
But wait a second, isn't the three-body problem already a chaotic system, for example?
Oh yeah, three-body problem as well.
Right. So that would be an example of I think this should be a chaotic system. I don't remember if it's a chaotic or it just doesn't have analytic solutions, because those are two different problems. Yeah, but yeah. Anyway, so the point is that you don't need mechanics to be able to talk about dynamical system. You can have dynamical system without mechanics.
Right.
Okay.
Okay, we'll close it if there's no other questions. Thank you, Miguel, for
Yeah, I had a
participating.
small question.
Oh
Sorry.
yeah, go ahead.
Yeah, are there like, I mean, when we saw the Venn diagram, I think there was a very large, I mean, there was a huge difference between the Newtonian and the Lagrangian. Like, you found a lot of systems which didn't have an intersection. Why is that so?
We already said that before. Like, you should probably go and look at the previous live. So the point is that when you have an n degrees of freedom, you
Yeah.
need n functions of position and velocity and time to describe the forces. You have one force for each independent degrees of freedom. When you have a Lagrangian system, you only have one functions of position, velocity, and time.
Yeah, the two n differential equations.
What?
The Euler-Lagrange equations are two n differential equations, right? For n differential,
No.
for n.
The point is that given one single Lagrangian, I've already specified the motion of the system.
Ah, okay.
Well, the other one, I need n functions of position and velocity.
Right.
Even for just one particle, you could just have like a Lagrangian is just one scalar function. It gives you one number.
Yes.
And then for a force, you would have three independent components in principle. And like
Okay.
three
Yeah.
independent components for the three directions, or just one Lagrangian, which is one number. Like you cannot find a continuous like map from Lagrangians to
Ah,
functions. You will always have some functions that do not come from Lagrangian, which is, I guess, exactly the ones that don't have potential.
right.
That's it.
Yeah. Okay.
Oh, yeah.
Okay, so we'll stop it here and see you next week.
See you. Bye.
Right.
Okay.